Hey guys, so in the next couple of sessions, I'm going to be talking about virtual machines and in Azure. And virtual machines in Azure typically work with networks in Azure. So before I get into the virtual machines, I'm going to be talking about networking. And networking requires an understanding of a concept called Cider and Cider ranges, right? Which is a technique that's used in Azure and in networking in general, I should say, to determine the number of IP addresses. And if you don't understand IP addresses, then go and research that somewhere else. And then once you sort of get a sense of it, come back and continue this video. But it's a way for you to identify how many IP addresses are essentially available to be used in a given network. So that's what we're going to be talking about today. And what are cider ranges and where do they come from, right? So back in the day, if you've been using computers for long enough, they had this idea of something called a net mask or a subnet mask, right? Which essentially was a set of numbers that are used to define what the available space within a network is, right? So I'll take it one step back and I'll say what we're discussing here is IPv4. And IPv4, you basically addresses are identified in this way, right? So I'm going to put 0.0.0.0.0. So you want to think of it like a counter that starts here at 0. And this one counts from 0 to 255. So altogether, this 0 has 255 slots. As a matter of fact, I'll draw it like that, at 0. So underneath 0 to 255, right? And the same thing over here, 0 to 255. The same thing over here, 0 to 255. And ultimately the same thing over here, 0 to 255, right? So if you think about it like a counter counting from right to left, this counter basically will go to 255. And then once it completes one round to 255, this turns to 1. Then this goes back to 0, right? So this will go to 255 and turns back to 1. Then that goes back to 0 and starts counting once again to 255. And that goes to 2. And this goes back to 0 and it starts counting and on and on and on. So basically there will be over here, it'll be counted from 0 to 255, 255 times, right? For this to hit 255. And you can always tell what this counter over here is, because this is a count of how many times, I'll use a different color, this area here has gone to 255. So if you see an address that is 0.0.5.0, right? That means that this has gone 0, 1, 2, 3, 4, and it's now on the fifth one. So in the 5, right? So it's starting the fifth one. So it's gone 5 times already. Because remember, these are 0 index. They start at 0, as you can see. So 0 was the first, 1 was the second, 2 was the third, 3 was the fourth, 4 was the fifth, right? So pretty straightforward. So obviously, one of the things that you can see from here is that in the same token, when this is at 0, when it goes to 1, it would mean that these two numbers have gotten all the way. This has gone to 255, this has gone to 255, and then it got zeroed out. And when both of these zero out from the sequential counting that's going to happen, that turns to 1. And then the same thing happens here as well, right? So that's the general structure of the IP addresses. So when you see an IP address that, let's say, says 192.168.5.7, note that the numbers that show up in your IP address are never going to pass 255, because 255 is the max that can show at each slot, right? So what is a net mask? Now we sort of understand what an IP address is, right? So a net mask, like any other mask, what is a mask used for? Masks are used to cover parts of, traditional mask is used to cover your face in one form or another, right? There's masks that just cover your eyes. There's masks that cover your eyes and maybe expose your mouth. There's masks that cover your whole face. It's a mask, right? So the mask, if you take that and overlay it on networking, you can think of a mask as something that depicts the areas in your network that are covered or unavailable, right? So in the old days, you might have a subnet mask that looks something like this: 255.255.255.0. So what is this saying, right? So each segment of the subnet mask essentially tells you how much of that particular segment is available, right? So in this case, if it's gone up to 255, it started at 0 and went up to 255, that clearly means that there are no addresses available here. If the same thing happens, no addresses available here, same thing happens, no addresses available here. And then finally over here it's 0. And what's this telling you? Well, it's at 0. So I can start from 0 and I can go to 255. So this address space basically allows that last segment, no matter what appears here, that last segment has 256 available IP addresses, right? So if any network, right, if I have a network 192.168.5, right, what can an address that fits into this space be? Well, it can be 7, can't it, right? All right, or it can be 1, right? Or it can be 200 and it can be 248, right? It can be any of the available addresses that have been depicted here, right? So let me just move this over a bit. There we go. Having a computer slow down day here. All right, so it's any one of these addresses, right, would fit into this 255.255.255.0. Well, what if you had an IP address that was, or a subnet mask that was 255.255.255.10, right? Well, that would mean that those 10 addresses have been taken, right? Or, from 0 to 9, 10 addresses have been taken, and you're starting with the 11th address, 10, and then you can go all the way up till 255. So using that same logic here, this address works, right? And this address does not, right? Because as you can see, 10 is greater than this 7 over here. So this net mask is telling you that your address space must start above 9. It starts at 10, and it can be inclusive. It can be 10 inclusive. So basically your address space can start at 10 and go all the way up to 255. That's the general gist of it. So that's what a subnet mask does. And this is not just here, right? So even if I had a subnet mask of 255, 255, 120, 0, okay? That's an address space that, again, is telling you what kind of addresses can go in there. And in this particular case now, this will no longer work because the address spaces that you can use would start at 120. So they can start at 250, they can start at, 192, 168, 120.0, all the way to 192, 168, 255.255. This whole entire range fits in here, right? However many IP addresses are, right? And this is a great way to represent IP addresses, but there's one sort of problem with it in terms of like actually giving you a sense. I mean, this works to let you know that an IP address is the kind of IP address that has the specific address spaces that's required, but it doesn't tell you any information about what the actual IP addresses are. So over here, if my IP address was 10.15.120.0, or my address was 192.168.125.248, because they both work, because the address space that we're working on starts at this 120. Whatever else is before the 120 is essentially locked out, so we don't care about that, just like the 192.168. We start from the 120, and it's from the 120 upwards, and then the range, the range starts at 120, and as you saw here, goes on. So it doesn't tell you a lot about what these values here should be, right? In a sense, it tells you that these values are the values in the network that cannot change, right? But it doesn't necessarily tell you what those values are. So enter CIDR or Cider ranges, and I'll just clear the screen here. And Cider ranges provide you with a sort of like an in-between. It will tell you about the IP address and also tell you about where it should be, what the range is that it's going to be, right? So how does the Cider range work? Okay, so a Cider range for that 192 address that we provided before might be 192.168. Let's go with 10.0. And if we wanted to start at, we won't use that. We'll use the 255 one up here. So we're going to map it to that, right? And if we wanted to do just this, right, we need a way to indicate that this last zero, to tell us the range, there would be a / here. And then in here is where we would specify what the range of the addresses is, starting at this 0. So it's going to start at 0, just like here, right? And it's going to go to a certain number. Now, in this case, where we're trying to go, we're trying to go to 255, right? So we want this to go from 196.168.0 to 196.168.10.255, which is how many addresses? Well, that is 256 addresses, right? So what's interesting about that number, 256, and here's where we're going to go into a little bit of exponential algebra. Don't be scared. It's pretty straightforward, is that you can represent this number 256, right, as 2 to the 8th power, right? 256 is equal to 2 to the 8th power, right? Okay. So to a certain extent, we can look at these net masks and these addresses, we can look at them as 2 to the 8 dot, 2 to the 8 dot, 2 to the 8 dot, right? 2 to the 0, something like that, right? Okay. So that's what's being sort of exposed. Okay, I don't want to get too fancy with that, right? So let's just get back to this, and let's say that over here we're trying to represent 256 values, right? And so these values can be represented either as 256, so we could literally put 256 there, right? Or we could put 2 to the 8, right? Now, we're using computers, right? And because we're using computers, we know that the bottom part, this 2 part, is always going to be there. Why? Because computers use ones and zeros, binary, right? That's where the power and the exponents and all that sort of stuff comes from, right? So down here, this part, right, the 2 part kind of can be implied. It's always going to be there. So in Cider ranges, what they do is they just use the 8 part, right? The 8 part, right? So the 8 part, that exponent part is what's going to potentially go up here, right? Right, to say that this was 2 to the 8. But remember now that IP addresses and net masks, if we go back to the net mask world, that they are not, they're masks, right? It's not representing what's gonna be there so much as it's representing what's not available to you, just like in the old world, right? Right. So in the old world of net masks, it typically represents what's not available to you. So let's rewrite this in terms of ranges, getting rid of the 2, right? And then showing how this is all built up, right? So over here on the leftmost part, right, the 255, using this mechanism, well, that can be represented as 8, right? Right? Because the first 8 bits, right? I'm not the first 8 bits, the first 8, right? 2 to the 8, the first 2 to the 8, right? Is basically unavailable, right? So then there's a dot. So what's going to be here, right? Well, going back to the old algebra, right? This is also 2 to the 8, right? So what is 2 to the 8 represented as? What does 2 to the 8 plus 2 to the 8 equal, right? So if I did 2 to the 8 plus 2 to the 8, right? You can actually represent this as 2 to the 16, right? And we can actually, yeah, I mean, you can open up your calculators and look at it, right? 2 to the 8 is going to be 256, right? Let's open up the calculator. There we go. So 2 to the 8 equals 256. And if we multiply 256 by 256, we end up with 65,536, right, values. That's the end value, right? Now let's go back and let's do just 2 to the 16. And as you can see, it's the same number, 65,536, right? So what that means is that you can combine these instead of representing, instead of representing it as 2 to the 8, 2 to the 8, I can represent this overall block as just 2 to the 16, right? And if I represent this block as 2 to the 16, it would mean that this part is completely blocked off, right? Using the mask, it's been masked, right? There's a mask over this part, right? And I'm representing that here, right? When you're showing the mask, you start the mask from the left to the right to show which parts are not available to be used, right? So once again, we start 2 to the 8 is not available to be used, and this 2 to the 8 is not available to be used. The reason why these are being multiplied is because, again, it's a counter, right? This value here on this side is 255 this many times, right? So 255 times is what this value is what this value represents, and that is 2 to the 16 as we previously shown, right? So let's take it one step further, right? And let's now add this section right here, right? So following the same mechanism, so we're now adding, right? So I'm doing add, but it's really a product of, right? So we're now multiplying, I should say, by another 2 to the 8, right? And so when you do that, you basically, when you multiply at the lower level, you add at the upper level. So in the first case, we multiply 2 to the 8. I'm sorry if I said add. We multiply 2 to the 8 by 2 to the 8. I meant you were adding the two ranges together, which is a multiplication. So in the first case, we multiply 2 to the 8 by 2 to the 8, which would then turn into 2 to the 8 plus 8, which is 2 to the 16, right? And that's what we have here. And we prove that that equals the same number as whether you did 255 times 255, or you did 2 to the 8 times 2 to the 8. It's the same exact thing. Or you did 2 to the 16. They all turn into the same value, right? So at the exponent, using the exponents, whenever the base is multiplied, the exponents basically can be added. So in this case, we're now going 8 plus 8 plus 8. So if we wanted to add this section here, right? If we wanted to add the next section here, use the fancy one, that's going to multiply another 2 to the 8, right? And, so now we're going to add plus 8, and that's obviously going to equal to 2 to the 24, right? 8 plus 8 plus 8, or 8 times 3 is 24, right? And once again, we can test this out by simply going to the 24, and that's how many addresses are being taken up when you add those three together. And you can do it the other way. I can do 256 times 256 times 256, right? Oh, didn't do that right. 256 times 256 times 256. And that gives the same number, right? 16,707,216, and then 2 to the 24, 16,707,216, right? So same exact value. And then the next step from that is then going over here, minimize this, going over here and adding that last range, right? And the last range is the last 256, and that's the total amount that a network can have, right? So you can actually represent this as 256 to the 4, because there's 4 segments, right? And that's the total amount. And that's the total amount that's available in an IP v4 range, because that's basically all the addresses. It's less than that because some addresses are reserved, so you can't actually work with everything. But in general, if you had, using this counting system, if you started at 0 and counted all the way up, that's the number that you would end up with. So that's one way of looking at it. Another way of looking at it is 256 times 256 times 256 times 256, right? You end up with the same number, right? And another way of looking at it is 2 to the, what's 8 plus 8 plus 8 plus 8? 8, 16, 24, 32, right? So 2 to the 32, and you end up with the same exact number, right? So when we want to add the last bit to it, we just add another 8, and then we end up with 2 to the 32, okay? And that basically now covers everything, right? So now everything is covered, and of course, there's no IP addresses available, right? So if you use this address, let's say I had an address of 192.168.5.7, for example, and the whole entire address space was covered, right? Then you'd effectively be saying that, that IP address, it's a single IP address. There's no range around, right? Now, of course, there's caveats to that, but in general, that's essentially what you're saying. Okay, so how is this represented? Let's go back here to what we're working on and how is this represented, right? So we already established that what we're defining is a mask, right? So we're not defining the parts of the network that are free. We're defining the parts of the network that are not free, right? We're starting with the parts of the network that are not free. So that would mean that this number, right? And we've already established that we're only working at the top part, right? We're only working at the top part, okay? So if you use just the top part, everything on the right, the entire address space of the right is 32. The entire address space of the rightmost next to that is 24. The entire address space here is 16. And the entire address space here, right, is 8. So you've got your 8 address, your 16 address, your 24 address, and your 32 address, right? And you work down from there, right? So what it means in terms of networking. Let's say that I wanted to define an address space I wanted to create a mask that covered everything except for the parts that I want to use. I would have to subtract, right, from this exponent number over here, the 32, the amount of space that I wanted to use. And then that space in and of itself, because we're working as an exponent, can be expressed as a factor, right? So it can be expressed as 2 to the n, okay, right? Where n represents what I want to subtract from the network, okay? So as it stands, if I wanted to show 2 addresses as an example, right? Because that's the lowest I can go. Well, I guess I could show no address, but 2 addresses, that would be 2 to the 1. 2 to the 1 is just 2, right? Right. So to show 2 addresses, I'm looking at 2 to the 1, right? So how do I represent that in terms of a mask? In terms of a mask, what it means is that I have to subtract this number from the overall number, right? The maximum is 32. So if I subtract 1 from this 32, I end up with 31, right? And to provide 2 addresses, right? This address space would be 192.168.10.0/31, right? This address would allow me to represent 192.168.10.0 and 192.168.10.1, right? These 2 addresses are represented by that. So what if I wanted to represent 4, right? Well, you guessed it. To represent 4 IP addresses, what is 4? 4 is 2 to the 2, right? Again, we're dealing with exponents, right? And then you take these 2 and you subtract it from your total amount of 32. And so in this case, you end up with 30, right? And I'll get rid of this, right? And so when you have 30, now I can represent the addresses that go from 192.168.10.0 to 192.168.10.3, right? So 0, 1, 2, 3, right? Those addresses will be available at 30. And the list goes on, right? Now, one thing that you'll note, and the next one that I go to, is the next one I'm going to go to. So we started at 1, and we went to 2, right? And the next one we're going to go to, obviously, is 3, right? Because you're always going to have to represent it in this form, right? You can't simply represent it you can't represent it in just anything. The blocks are set because we're working within address space and memories, and you're going to have to the architecture is base 2 base. So there's certain kind of values, a certain way that addresses have to be structured in such environments to capture everything. So just keep that in mind. So if we now went to the next level, right? So we now want to say, hey, I want to go down from 30 to 29, right? That's -1. So now we're dealing with 2 to the 3. Now there's something interesting about 2 to the 1 was 2. 2 to the 2 was 4. 2 to the 3 is 8. Okay. So if this is a 29 here, then basically that gives us 8 addresses. So what's important to note from that, right? One key thing to pull out of that is that each time you drop down by 1 in this number here, you must double, it doubles the number of addresses that would be available to you within that block, right? So that changes this to going from 0 to going to 7, okay? And on and on and on, right? Up until you get to 24, right? And when you get to 24, you use the technique that I typically use, right? Is to understand how many addresses are in there, simply take this value here and subtract it from 32, right? So 32 minus 24 equals 8. And then this value here, the resulting value, you essentially take it and make it the exponent of anything to find out how many addresses are in there, right? So you then take this value, so it's 8. So that means that the number of addresses is 2 to the 8, right? So this 8 is showing up here, which of course, as we've seen before, is, and I didn't plan this, but it worked out perfect, 256 addresses. So that means that when you do a /24, it's gonna take up the entire block, right? It's gonna go all the way to 255, okay? And that's Cider ranges. So let's clear this up right now and let's kind of recap. So now we understand how that works, right? And we understand the general mechanisms that are used to set up the address. So let's go back to our basic address. 192.168.10.024, which gives us 256 addresses, right? So obviously when we drop down, what does that mean? That's the question of the day, right? So if we're gonna go down to the next level of 512, right? Remember that 512 is just 256 times 2, right? So for you to go down, if I drop this down to, let's say I want to do 512 addresses, right? Because this is where it gets confusing. In the basic structure of it, it's not that bad. And I'll take a step back and explain to you what I mean. So obviously /24 would give you 256. The next one is if this goes from 0 to 256. So if you were at 192.168.0.0, and if I subtract 8 from it, then it's a /16, right? So that's going to give me that 65,000 blah, blah, blah number. And in Azure, that's the most you can do in a network address. But you know, just taking it one step further, if I just did 192.0.0.0, right? This would be a /8, right? Because I'm saying that, you know, the mask is covering just this part, right? Remember, the mask is covering this part, the mask is covering this part, right? Okay, even though that says 10, the mask, you know, this is where that whole thing about a subnet mask not being this being superior to a subnet mask in the sense that even though is that I'm providing both the way the IP address is going to be structured, the actual numbers that it will have, and I'm providing the range, right? You can't do that with a subnet mask. So I couldn't, for this Cider range here, use something like 10.200.0.0/24, right? That does not, or actually just get rid of it, right? 10.200.0, that doesn't work here. Even though a 24 address can be created out of this, right? Because this part is a 24 address. The rest of the Cider range does not match, right? This is 10, this is 192, this is 200, this is 168, right? So the rest of the address range doesn't match. So the good thing about using a Cider range is that it allows you to sort of like cover both ends of the spectrum. You can give a very concrete IP address, and you can also provide the range, you like fill in the blanks. So here's the beginning, and here's the part that here's the part that you have to use, and here's the part that you can have some variance with, right? So then obviously an address of 0.0.0.0 has no mask, right? So this would be a /0, right? That says, hey, everything, there's no mask. Everything in here is viable. And I want you to remember that, right? Because again, Cider ranges are used all over Azure, all over networking. And there's as we get into the networking, we start creating, you'll start to see this occur, right? You'll start to see why, where this is relevant and why this is actually a possible Cider range, even though it's not an address range that you can use to create a network and say, hey, this network is this size. It is a range, right? Everything is something. Like if I wanted to, let's say I had a firewall and I wanted to I had a firewall that was blocking, that basically blocked traffic in, and I was using a Cider range here to determine what kind of traffic would be allowed. Well, if I had this address here, then it would allow any IP address that started with 192, right? If I had this address here, it would allow any IP address that started from here. If I have this address, the same thing. What if I had this address? Well, what does this mean? This means there's no mask. So everything will flow through, right? So it's important to understand this, right? So just get rid of that. So that's the general structure. So here's the basic fun part, right? But what now starts happening is if you create Cider ranges that don't fit into this mode, right? Because there's, we've already seen it actually, right? So if I used 25, right? If this was 192.168.10.0/25, well, what is 25? 25 is 2 to the what? 2 to the 7, because 24 is 2 to the 8. And what's 2 to the 7? I believe 2 to the 7. The easiest way to do it is to do what? Take 256 and do what with it? When you go up by 1, you multiply by 2. When I go up by 1, what I mean is that the mask area is reducing by 1. The mask area is getting smaller, right? Right? And the address space you have is getting larger. So your address space is going up by 1. So you multiply by 2 to see how many addresses you have. When you go down by 1, means your address space is getting smaller, the mask is getting larger, right? And so what you do is you divide by 2. So if 24 is 256, without us doing any mask or flying out the calculator, 256 divided by 2 equals 128. So that would mean that there's 128 addresses. So that would mean that this address space can go from 192.168.10.0 to 192.168.10.128, right? I'm sorry, 127, right? Because 0 is an address space, right? 0 is one of the addresses, right? So that's all the addresses that would sit inside of a /25. But what if you wanted to create multiple addresses, right? What also fits into a /25? If I wanted to put another address space, another subnet, another area, right? So I have one range and I want to create another range next to it. This range is completely blocked off, right? If I wanted another range, I would have to start my count at 192.168.10.128 because that's the next available address, right? And then this guy can also be 825, right? So you can always fit two of the item of the range you have. If you go down by one, you can fit two into it because you're dividing by two. If you don't go down by two, you can fit four into it. So if I now turn this into a 26, then a 26 is what? It's 128 divided by 2, so that's 64. So I can create four addresses, right? Four address spaces within that range, right? I can create one that goes from this to 63, one that goes from 63 to, and so this is the first one that goes 63. Then I can create another address range that starts at 64, and it's also a /26. I can create another one that starts at 128. And finally, I can create one that's also a 26. And finally, I can create 192.168.10. I think it's 192. Don't quote me if I'm wrong, right? That'll be the last one. You can fit four in, right? And just like that, you can't just fit four. You have to think about it in cool ways. You can also potentially fit three in, right? Two small ones, so 26, 26, and one big one, right? So I don't need this, and I just keep this as 25, right? So this is gonna give me altogether 128 because it's 64 and 64. And then this is also gonna give me 128, right? Right. And then that covers the full 256 range that's associated with this IP address, this area right here. Right? It's 256, right? Oh, no, got the wrong way. So get rid of that. Ooh. Okay, so the actual address range will be, so the actual area that's being covered is so like that. There we go. Okay. So that whole entire range is being taken care of by three addresses. And you just have to think logically about it. Again, the key things to do is remember it's 2 to the, right? And remember that each one is 256, right? So this is 256 altogether. And then over here is the next level. The next level is basically that 65 goes all the way, takes that 256 all the way up to 65,000, right? So what if what if it bleeds over, right? So far we've looked at within that range, but bleeding over is no different, right? So let's say we wanted to show so we now showed a /24. What if we wanted to show a /23, right? So a /24 is 256, right? A /23 is equal to 256 times 2, as discussed, which is equal to 512, right? So the hint in this is this right here, right? Because remember, if you go back to our old discussion, that this is a counter, right? This over here, you can think of this as a clock, right? So the math for this is actually represented visually here with these dots, right? Which you can think of as products in the algebraic nomenclature, right? So what does that mean? So what it means is that I can represent 512 as 2.0/, 23, right? Right? Because this is going to go up to 256 once, right? And then it's going to go up to, for the first one, right? That's going to change it. So it starts at 0. Let's just go through and look at it. So it's 0.0, and I'm only looking at this part, guys. I'm not showing the rest, right? So we're at 0.0, right? And that's going to go all the way to 256, right? And then the clock is going to flip, and it's going to go to 1.0, right? And that's going to go all the way to 256. And that's the two addresses, right? Actually, it's not 2.0, right? So basically, the next address after that, right? After everything is done, once you have your full 512 address spaces, the next address after that will be 2.0, right? So if I take this and I represented it in a Cider range, I could do 192.168.10.0/23. All right. 10 is going to be the first one, right? That's going to give me 512. I'm sorry, that's going to give me 256 from here. And then 11 is going to be the next one. That's going to give me another 256, right? Equating the whole 512, right? So 10.0/24 and 11.0/24 is equal to the 512 IP addresses that we're talking about. And you can actually represent that just by doing 192.168.10.0/23. When I put that in there, it means that I'm going to count up by 2 here. And I'm going to, because I'm going to count this twice to represent 512, right? So that's the basic flow, and that's the basic approach to Cider ranges. That's how Cider ranges essentially work. Again, in Azure, I'm breaking it down into Azure. There are a number of rules. You can't do a /32, right? Because that doesn't really mean anything. Because they only deal with ranges. A /32 is basically just the IP address that you're interested in. Everything is taken up. Just like a /0, 0.0.0.0/0 essentially represents, everything. The /32 represents nothing, right? So everything is essentially masked, right? That you're representing the whole entire address range, right? In that particular area, right? But it's not as I don't want to get into that too much because it's not as it's not going to come into play in terms of what you're doing. Okay. So in general, that's it. So one of the things that you need to remember about Azure is that, once again, I'm going to switch this over yellow, is that this is the largest range that you can have. Okay. Now you can have multiple of them and create a very large network, but the network is locked into that range. And remember, this is 65,000 IP addresses. That's a lot of IP addresses, right? Most of the time, you're going to be dealing with /24s, right? And if not /24, maybe 23, maybe 22, right? So 22, we can do that math just from 24. That's 256. 22 would be basically multiplied by 4, or multiplied by 2 twice. So that would give you altogether. So if you had a /22, that's equal to, I think, 1028, right? So it's 512 times 2. All right, so that's basically it. Now, if you have any questions, once again, reach out to me on Twitter, Instagram, all the social medias, CIDR ranges are awesome. Try them out. Go on your Azure portal and play around with them and see And the great thing about Azure is that it will actually create these for you, or show you the actual addresses that fit into that range, so you don't have to do all the math that I did here, much guesswork. So take a look at that. In our next video, we're going to get into networking, and we will be showing you an actual representation of them and showing you how this works inside of Azure from a networking perspective. So we will see you in the next one. Have a blessed day.